Welcome to the third session of the day, and I would like to request to Professor Fowler to chair this session. Sir.
Yeah, welcome back. So the first speaker in the afternoon session is Malay Mandal from IMSC, and he's going to speak on the topic is title of the lecture is compact quantum semigroup structure on the non-commutative unitary sister algebra.
Thank you, sir. Thank you, organizer, for giving me this opportunity. Okay, so I'll start with very basic definition called sister algebra. So basically, sister algebra we can define many ways like abstract and concrete way. So one can think sister algebra is like a sister algebra is closed non-closed star subalgebra of B of H. B of H means bounded linear operator space on a Hilbert space. Okay, so basically my talk title suggests this compact quantum semigroup structure on some sister algebra. So basically I want to start with like motivation and very basic definition of what is compact quantum group actually. So if you have a group, let's take a compact topological compact Hausdorff group. Then we have a composition like from G equals to G. Then one can like extend like these things to functional level. So one can have a map from CG to C G cross G. So if you take composition here, so here actually one can define delta. Delta is going like F going to delta F, acting on X, Y, F of X, Y. Okay, so with this map, one can like also, okay, so these things actually one can say that this is isomorphic with CG tensor CG. Here like tensor is tensor product sister algebra, and there are a lot of tensor products, tensor norm is there. One is, this is actually we are taking minimal. So for CG, everything is same actually. Minimal, maximal, everything is same. Okay, so this with this map, one can prove that this delta tensor identity delta is this is as a star homomorphism, as star homomorphism. And second thing, one can prove that one tensor CG delta CG and CG tensor 1 delta CG is are dense in G tensor CG. Okay, so actually this delta satisfying both true conditions, and one can see that this CG is actually a commutative sister algebra. So one can want to define for non-commutative setup. So for that, one can define what is compact quantum groups actually. So for that, in general, compact quantum group is a pair A comma delta, where A is a unital sister algebra, and delta is a map from A to A tensor A with satisfying two conditions. So if you take A equals to CG, okay, let us take like delta tensor identity delta and second condition is this is called co-associative, and one is called delta A, and one tensor A delta A are dense in A tensor A. So if this satisfying these two conditions, then we will call A comma delta is a compact quantum groups. Okay, if this satisfy only this condition, we will call it compact quantum semigroup. and this condition called cancellation law. Okay, now so this notion actually was deduced by Ornochis in 1987, and he called it from like first he called it compact quantum matrix pseudo group. Later, actually, many people derived the notion and we called this like compact quantum groups. Okay, now in our case, as we want to see the, so for example, one can see that C of G itself is a compact quantum group if G is a compact Hausdorff space. And another example is if you have gamma is a discrete countable group, then this is actually also from a compact quantum group. This is also a compact quantum group. So we will denote by this. Okay. In our case, this sister algebra, non-commutative unitary sister algebra. So we denote it by UNCN. NC stands for non-commutative. This is actually universal sister algebra. Sister gamma is full group sister algebra. So you have for gamma, you have a group ring. On a group ring, you from the group representation, you can extend to the group algebra level. Then with respect to that norm, if you complete it, we'll get that full group sister algebra. Okay, that is actually full group sister algebra. That is denoted by sister gamma. Okay. Now UNCN is a universal sister algebra, which is generated by Uij such that, and this relation is like satisfying this matrix is unitary. So now, so this sister algebra actually started by Brown, and then further like lot of studies by Kevin McLean, and he proved like very important result that this sister algebra one can embed it into a free product of sister algebra, that is Mn star Ct. And this is actually isomorphic with commutant, relative commutant of Mn. So one can see that UNCN has also a free product structure here. So it has a lot of things can do like, so for that one try to understand whether like any semigroup, compact quantum semigroup structure is there or not. So once actually proved that this UNCN admits compact quantum semigroup structure, but it is not a compact quantum group. So let's see how. Okay, so because of this universal sister algebra, it is a universal property. So universal property like that, if A is another sister algebra and Vij belongs to A and Vij is unitary, then there exists a unique star morphism pi from UNCN to A such that pi of Uij is Vij. So this is the universal property for this universal sister algebra UNCN. And using this universal sister algebra property, one can show that this has a semigroup structure. Like if Uij is unitary, then one can show that by hand actually, like Uik tensor Ukj, if you take ijth position is this is also unitary. Unitary in Mn of UNCN tensor UNCN. By universal property, so we have a map delta from UNCN to UNCN tensor UNCN such that Uij is going to Uik tensor Ukj. And also note that identity in MNC is the unitary matrix there. So also we have a epsilon map from UNCN to C such that Uij is going to delta Ij. Okay, so basically one can give that it is a monoid quantum monoid structure on UNCN. but this is not a compact quantum group. For that, we need one result. Like if U belongs to Mn of A, so we are taking as a compact quantum group. If U is a representation, like unitary representation, means U is invertible, and delta of Eij is U ik tensor Kj. If A is compact quantum group, then U bar, that is defined by Uij star, that is also invertible. So this is the result. Using this result, one can prove that UNCN is not a compact quantum group. So how? For that, let us take UNCN is a compact quantum group. Okay, then its generators is a unitary matrix. Already you have seen by definition is a unitary matrix, and also it's satisfying this condition, like delta of Uj equals to Uik tensor Ukj, and one can think that in M2 MNC, one can think this matrix actually unitary matrix. Unitary matrix is Mn of M to C. Like each block is 2 by 2 blocks, and this is unitary matrix. So by universal property, we already have like Uij is going to like here actually in M to C, we have a star morphism. If this is a compact quantum group, so this is invertible, already unitary. So so by this condition, Uij star is also invertible. If it is invertible by this pi map, that pi of Uij star also should be invertible. This matrix should be invertible. But if you see that this matrix, if you transpose this is not an invertible matrix. So this has a no compact quantum group structure. Though this is not a compact quantum group, so we are able to prove some structural property like spectrum of this. So basically, Wendell proved that for a classical case, if G is a compact group, then only invertible element on, so take probability measure on G. Set of probability measure on G. So only invertible element in P of G is the direct delta measure. Direct delta measure means like on point set. And direct delta measure corresponds to on the functional level from CG to C is a functional, like evaluation functional. Gamma x is f of x. So this is if and only condition for the classical case. So we want to see for the compact quantum group case. So whether like our theorem is that like if phi from UNC N to C is an invertible state, then like our question is whether this is the character or not, because one consider for classical case this is characters. Then we prove that this phi is character. Invertible state means okay. So on UNCN, the state means like a positive linear functional from UNCN to C. This positive means take all positive element going to positive. for all A in UNCN. And here actually one can give the product structure on S of, so we denote this state by S of UNCN. Then phi and psi, if two element in S of UNCN, so one can give a product structure here. That is phi tensor psi composed with this co-multiplication. This is like product measure on the classical case actually. So on here, also we have seen that it is a co-unit, that epsilon co-unit there. So one can give that invertible notion here actually. So with that invertible notion, if some state is invertible, and also one thing, phi of 1 is 1 because of state. If invertible, then one can prove that phi is character. Character means one-dimensional representations. Okay, so how much time? Okay, to prove actually not that chart. To prove that, sorry. No, not a mu, not even. It cannot be invertible. Infinite dimensional is finite dimensional. So, okay. Okay. Now proof. For proof, we need this lemma. This lemma is proved by myself and Ishan Patri, that if phi from a C star algebra to C is a state, and we have proof for general case, but here we only need this this type, this structure, and let's say Uij, let's say Vij generates A as a sister algebra, then if Vij also unitary, and if it is implies that phi of Uij is unitary in MNC, then phi is a character. Okay, this result we have used. So one can see that from linear map we have star morphism actually because of this condition. Okay, so using this result we are going to prove that any invertible element is characters. So for that, okay, as phi belongs to S of UNCN is invertible, then there exists psi in S of UNCN such that phi star psi and psi star phi is epsilon, that characters. What this notion, this is actually if you act on Uij element, that delta of Uij, that will give, so this is like epsilon of Uij, and this actually give you phi of Uij, psi of, sorry, Uik, psi of Ukj, k equals to 1 to n is delta of Ij. So this is true for all Ij. So this actually implies phi of Uij and psi of Uij is identity. So basically from there we got phi of Uij is invertible in MNC, but we have to prove that this is unitary. So that is also easy by on just observation. So as phi is state, so phi is also completely positive map, unital completely positive map. So one can define like phi n from A to C. One can define also phi n also mn A to mn C. At the point evaluation, like phi of xij is going to phi of xij. So and as this is a state, so one can prove that this is also like norm 1 positive functional, norm 1 positive functional. So norm of phi n also less equals to 1. So using this result, so one can prove that. So we want to prove that this is unitary. Phi of uij is unitary. So for that, take any element, then this norm is actually less equals to x. So for x belongs to Cn. And for the other side, we just compose with psi of uij. And because of this phi and psi both are in state, so we have this result that this is isometry, and in final answer isometry is unitary. So that's why phi of uij's matrix is unitary matrix. So for that, this is a characters. And also for compact quantum, so this result can be extended to the compact quantum group case also, because of multiplicative domain argument is there. So one can extend. And for compact quantum group, we know that like characters are invertible. But here UNCN is not a compact quantum group. Still, we can prove that all characters are invertible in UNCN also. So that's in general character, you have to define notion, product notion there, because in compact quantum groups notion is there, product notion actually. So, then I don't think for compact, because there are structures there, multiplicative domain and unitary, everything is there. So for that one can prove actually. I think proof actually, one can prove that. Yeah. Yeah. Yes, yes. That is like if you take any tensor product, like tensor product sister algebra is there. No, CGS sister algebra. One can make it CGS sister algebra, set of all continuous function, and product. The product is multiplication actually. Like f and g are from CG. Then f dot g, x is f of x, g of x. And the star structure one can give f of f star acting on x is. Yeah, tensor product on. No, but we are taking on algebra level. So from if you have CG A, B to sister algebra, then we have a tensor product of vector space on there as a tensor product vector space, and then on there one can define product structure there, like A tensor B and C tensor D. One can define AC tensor BD. And then again on this algebra and also star one can define by taking A star tensor B star. So star algebra structure on there on is A tensor B. And on the star algebra tensor, one can take a lot of like representation on there from there to B of H, and then one can like define what is the norm there. With respect to the norm, one can define the tensor product of sister algebra. Tensor product of sister algebra can be done. Yes. Not a problem. Yeah, Hilbert space is done. For Banach's, I think we have to take care of a lot of things actually. Yes, yes. And just that you are telling that G of G cross G same as. That is for Stone-Source's theorem. One can prove that CG tensor CG is isometric to C of G cross G. And the tensor product there you can take like lot of tensor product is there, but also same because CG is nuclear sister algebra. Like all the tensor product will be same there.